Hello and welcome to our talk, a research talk on methodical bias collection and reuse in deep reinforcement learning, which is a paper submitted to ALA 2022 workshop. This is Sahir, and it was a collaboration of me, Arjuman, Shajita, and Matt. So I'm going to go through the background, motivation, previous work, the goals and contribution of this work, the experiments, and the conclusion and future work. So background motivation, first of all, just to outline the scope, this work lies in the intersection of online reinforcement learning, transfer learning, and multi-agent reinforcement learning. So action advising literature, specifically in multi-agent reinforcement learning setting, is focused around student agent being held by a teacher agent. So a real world example would be a student or a kid, for example, a 2-year-old that has been taught by a teacher, by their parent, or for example, a professor. So bringing that idea, the real life phenomena into research, where the goal is to increase the sample efficiency of a deep reinforcement learning student agent, along with the presence of a teacher. So some of the previous work, this all started with Klaus in 1996 in his PhD thesis. He integrated apprentice learning and reinforcement learning. So what he did show was that the learners or students, he called learners, achieve better performance if there was a presence of a teacher that was guiding them through the states and providing actions to take. So they perform better than their counterparts where they did not receive any kind of training. So learners that perform better were the ones that were aided by the teacher. Moving forward in 2013, Torrey and Taylor proposed a teacher-student framework with multiple heuristics that were teacher-driven. So teacher is going to decide when to provide advice, and one of them were early advising. So what is early advising? So early advising is a phenomena where you have a teaching budget, B, which is pretty common in the action advising literature, which kind of gives a flavor of real world because the teacher is going to be available for a limited amount of time. Teacher can be costly to obtain. So B represents that number of actions that the teacher can provide at a given amount of time or in a given setting. So B is the number of actions. So that's limited. And in here, asking for advice or the teacher providing advice means the same thing because it starts in the beginning of training and exhausts until the budget runs out. So whether the student asks for advice or teacher provides advice are the same thing. And it runs until the budget runs out. So in the beginning of training, students going to be aided and then it's going to be on by its own. And one of the assumptions in this literature is the student doesn't know the teacher's algorithms and or parameters. So it's a black box to the student agent, the teacher. Moving forward in the literature, RCMP requested confident moderated policy advice by De Silva et al. In 2020. They proposed an uncertainty-based teacher-student framework where the student would ask for advice, action-wise, when it is uncertain. By uncertain, meaning that for a given state, its uncertainty is at. Now on the left, the diagram taken from their paper. So there's a set of inputs that passes through the hidden layers, and the idea was to modify the architecture to have multiple heads computing the same key values for a given state and all the available actions so that you get multiple data points to compute variance of the Q values across the heads, and then average that with respect to the actions to get an uncertainty for a given state. And if the uncertainty is high, the student is going to ask the teacher for advice. This was taken forward in the advice reuse realm, where we just not take the action and implement it, but allow the flexibility to have that action being reused somewhere in the future. So for example, you might sit in a lecture and then go home, but you can also sometime later, if the session is recorded, open it again and go through that if you want to revise things, right? So you're going to reuse that lecture. So similarly, that idea was proposed by Sahir et al. In 2020 for tabular RL setting, and some of the heuristics. And one of the heuristics actually that they proposed was DK reusing probability, which is a heuristic to enable flexibility for the student to decide between asking the teacher, reusing advice, exploiting his own action, or randomly exploring, or any other exploration strategy. So these 4 actions, with respect to their probabilities, were used to decide what exactly the student is going to do. But this was for tabular setting. Moving forward in literature, Elhan in 2021 proposed a new method called advice imitation and reuse, AIR, which uses a supervised learning model of the teacher. It captures the advising data between the teacher and the student. So this is a supervised learning neural network, and it's going to be trained on whatever happens, the communication that happens between the teacher and the student. So building that model, and then they use dropout to compute the uncertainty, which is U of M here. And then that's used for asking the teacher for advice, and also on deciding whether to provide reuse to the student. So the number 1, model is going to ask for advice if the uncertainty is high. Teacher is going to provide advice if there's enough budget. Number 3, student will ask for reuse sometime in the future. And then the model is going to provide advice if it's uncertain, if it's certain enough. So if it's certain enough that its uncertainty falls under some threshold, it will provide advice, and the student otherwise is going to follow its own action. So it has that flexibility. And as I mentioned, the dropout is used as a way to compute uncertainties here. Not to be, just to be sure, not to be confused, the model is not a model-based reinforcement learning. It's the model is just a supervised learning neural network. Moving forward, the goals and contribution of this work. So some of the limitation of the previous work is that it require a change in the RL agent architecture, like heads, dropouts, and there is a need of a specific domain-specific uncertainty threshold. So these are some of the limitations of computing epistemic uncertainty, which is the uncertainty that reduces over time with respect to the data that's collected. So it's reducible by the agent once it gathers more sample from the environment. So we propose a new way of computing epistemic uncertainty. And how do we do that? We propose a secondary neural network, which is trained with the agent environment interaction, and it is equipped with dropout. So we compute the uncertainty using this network with specified number of forward passes. So for example, 100 forward passes, and then use those 100 examples to compute the variance in the uncertainties. This way, the main RL agent architecture of the student is left unchanged. So the idea is the student agent can be any RL agent architecture. It doesn't have to be modified now. So if you have a new secondary neural network, which will be a proxy for the uncertainty of the student RL agent. So that way we keep whatever algorithm we want to test. We just have a secondary network that can be changed with respect to whether you need the uncertainty or not. So the goal of our work is to reinforce the idea of advice reuse, that teaching budget is limited, and capturing the advising data and then later reusing it should be a flexibility and a functionality enabled. And it allows for the help or aid for an extended period of time once the advising budget runs out. We also with this work build a methodical action advising framework that allows a student to request based on his own uncertainty, not by the model of the teacher, for example. So student can ask the teacher by its own uncertainty, and then along with that, we use the uncertainty of the model of the teacher. Work. So here we're dealing with 2 uncertainties, one for the model of the teacher and one for the student itself, which is being proxied by a secondary neural network. So that's the new way of computing uncertainty by having a secondary neural network that is separate from the RL agent, and no more changing RL agent. So the new way goes like this. The new way of computing epistemic uncertainty, we compute this matrix F, which is composed of different number of forward passes, so n total forward passes, and we have capital A actions available. So we get n by A metrics with q values, and then We compute the variance and then divide it by the number of actions to get that. Similar to what RCMP, is doing, but just doing it with dropout and number of forward passes and not changing the main agent architecture. So a methodical action advising framework that we introduce is the formulation is that the student learns a policy by S with the help of a trained teacher policy by E. The teacher can provide advice for a limited teaching budget B. The student agent can ask the model of the teacher and Omega for advice reuse, and the model of the teacher will provide reuse if it is certain. So these are only for the air and the SUA air that later will come in. So these are two relevant for that. And the goal is to learn optimal policy that gets as close as to an optimal policy for the student. So first baseline that we introduced is student uncertainty-driven advising. The idea is the same as in the literature, but the way of doing it is just different. The student agent asks the teacher for advice in states where it's uncertain. So UFS is computing using the newly proposed method. A percentile is set to compute the uncertainty thresholds C1 dynamically, so it's not fixed. And then the percentile is fixed. So the way the uncertainty is computed across the entire experiment will be changing dynamically, but this percentile that is used to calculate the uncertainty is fixed across all our experiments. This dynamic threshold C1 helps to decide when the student is uncertain. And this percentile is a parameter that can be changed. And here on the right, the C1 is being dynamically computed. It's not fixed. It's just dependent on the percentile hyperparameter, but it changes as the training proceeds. B is a constant, which is the teaching budget. Another model that we introduce is SUA AIR, which is on the right, we have the model of the teacher. Now AIR involves training a model of the teacher from advice interaction data. So adding AIR to SUA, which is the previous method, we get the functionality to reuse advice. So we ask the teacher for advice in cases of uncertainty. The teacher provides advice when there is enough budget. The student can ask otherwise the model of the teacher, and the model of the teacher can provide advice if it is certain. So combining both the previous method and the current method, the previous method and AIR, so we get SUA AIR. So it can either ask the teacher if it's uncertain or the model for reuse if no advice provided, or it can follow its own policy. Experiments that we conducted had 3 research questions. Does using 2 uncertainties help achieve adequate performance? And how well do these agents perform against the baseline? And what changes do the proposed agents bring to the advice collection and reuse process? So we tested on these 5 games, and the student agent algorithm is a DQN with modifications of double DQN with dual output. And that's the same for the teacher as well. And along with the secondary neural network that we used to estimate the uncertainties for SUA and SUA AIR. So the agents we tested were no advising, early advising, random advising, advise imitation, and reuse. Students uncertainty-driven advising, student uncertainty-driven advising with advice imitation and reuse. And so the results in general show a trend where advice reuse agents, so AIR and SUA AIR, perform significantly better than their counterparts where there is no advice reuse, but the results are not statistically significant against for SUA AIR compared to AIR. So along those two, the results are not statistically significant, so no claims can be made there, but across different experiments, different domains, we see a clear trend where usually the advice reuse agents perform better. And one example here is in the intermediate stages, AIR and SUA AIR achieve a performance that no advising agent achieves at the very end. So it's like a 1.5 times speed up, just to take an example. On the bottom, we have billions of random steps. On y-axis, we have evaluation score. And here on the right, we have the number of advice reuse and the number of advice taken. Moving forward, similar is the case for Freeway, similar trend. And the advice reuse and advice taken schedule pretty much remain the same, where the advice reuse for AIR is significantly higher For SUA error, the devices are reused less, but does not impact the performance. Similarly, in Qbert, things catch up at the very end, and in Sequest, we see the same similar trend where SUA also does better towards the end. And in Dero, we see that similar trend in the initial phase, that it does better than a new advising agent. But at the end, random advising agent does better in this particular game. So investigating the similar performance of SUA and SUA error, since the results are not statistically significant. So we evaluated the accuracy of the model of the teacher on Pong across 2 runs, and we saw percentage of correct actions being very similar, which somewhat shows why SUA error and error perform very similar. And the common denominator is the model of the teacher, which is pretty much performing in the same fashion. And then so that's why it's performing similar and not super better than SUA is not super better than error. So some of the findings with the results is device reuse is important, and it helps boost performance in RL agents in general. However, it cannot be said that SUA is better than error. Lastly, the conclusion of future work. So advice reuse is important for RL. That's the main takeaway. And methodical action advising framework is something we proposed in this effort. And we showed the systematic use of 2 uncertainties shows an improvement over previous work. It is not statistically significant, but it still is an improvement. And we also showed a new way of computing uncertainty that allows for less restrictions on agent architecture and parameters. Future work can involve extending the decision-making process by allowing advice to be reused during teaching, by preceding the student's decision based on uncertainty or advice reuse. We can also conduct extensive study on the reusing probability schedule. So there's a current delay in the decay that happens over time for advice reuse. So over time, the probability of reusing will go to 0. So this can be extensively studied. And another engineering effort could be to reduce hyperparameters. One key takeaway is advice reuse is online, ongoing, and overriding. It is important in RL. It is important for sample efficiency. So I request fellow researchers to start looking upon it and deep dive into it.